So now I'm going to talk about finding complex roots. So now that we have complex numbers, it means that when we have certain equations like this quadratic here, and we'll discover it's going to work with higher power models too, that under normal circumstances, if you were asked to find the roots of this, that is when this thing is equal to 0, you get x squared plus 7 equals 0, you'd subtract 7, and you'd long since know that you can't take the square root of -7. But now we can because we have complex roots. That is, in this case, it's going to be strictly imaginary, but there's still a complex number. Now, it does mean, and you'll notice the plus or minus, when you take the square root, we do get our two solutions. It does mean when you're looking at complex roots, we're going to get plus or minus, and okay to write that, square root of 7, or root 7i. So this means that there are indeed two roots. Now, I should probably point out that when we have complex roots, they occur in pairs, and they occur as the conjugate. That is, this is 0 plus root 7. Ooh, let's make that into a 7. 0 plus root 7i. That's one of the roots. And 0 minus root 7i. So what this means is these are conjugates of each other. When I say conjugates, more specifically, I'm talking about the real number portion is the same. In this case, it's 0, it's kind of bleh. The positive and negative of the imaginary part of that complex numbers. These always occur in pairs. And I should point out that this being quadratic, we'd expect two roots. We're always going to get two roots. So when we're talking about complex roots, we're going to be able to get as many complex roots as we'd expect, as we'd hope for from the polynomial. So a squared model that is quadratic is going to give us two roots. If this was fourth degree, then we're going to get four roots. We'll see later on that some of those roots might be real numbers, some might be complex. But whenever we have complex roots, they're going to be conjugates of each other, which means they're going to occur in pairs. Okay, another example. In this case, if you look at the discriminant of this thing, that is 2 squared minus 4 times 3 times 8. That is 4 minus, well, that's 12 times 8. 12 times 8 is 80 plus 2 times 8 is 16, 96. That's negative 92, which under normal circumstances means we can't solve this. That is, has no real roots. But we can find complex roots. And how do we do that? We use the, you guessed it, quadratic formula. So opposite b, aka opposite of -2, over 2 times 3, plus or minus. Now please notice this plus or minus. Now we know full well the b squared minus 40c is going to be negative 92. 2 times 3. So what we've got is we've got 2/6 or 1/3, right? I'm going to have to simplify this over. Now this is root 92i, and this is going to be 6, yes? In all honesty, what we could, now we can probably, I don't know, what we could pull a 46 and a 2 out. That wouldn't help us. But we could pull a 4 out, 46 and a 2. So that is actually 4 times 23, right? So what I'm doing is I'm reducing this. And so that way when I pull out the square root of 4, I get 1/3 plus or minus. So that's 2 root 23 over 6i. So 1/3 plus or minus 2/6 becomes 1/3. How convenient. I. If you wrote the roots 23, right? Now you could go decimal on me, that'd be fine, that'd be an approximate. But these are two complex numbers, 1/3 plus root 23/3 I, and 1/3 minus root 23/3 I, which means we have a pair, okay? So what this means is that we've got our pair of complex numbers, which we'd expect. The most number of roots we're ever going to get out of this quadratic is 2. There they are. Now this does mean one other important thing. If I were to tell you that one of the roots, one root of a quadratic is, let's say, 1 plus 3i, what do you know? Well, you know the other root is 1 minus 3i because they have to be conjugates. Now, even worse, this means because they're roots, you could write them as factors, right? which means you'd have minus 1 plus 3i minus 1 minus 3i, which means, you guessed it, you could distribute this. So you get x times x, which is x squared, and then you're going to have x times a negative this, so we're going to have negative x times 1 minus 3i, and then we're going to have a positive x times that's right, minus x times 1 plus 3i, and then we're going to have minus a negative, or plus 1 plus 3i times 1 minus 3i. There is a reason I'm doing this, and it's not just to scare you. When I distribute this, negative x, so minus x times 1 is minus x, minus a negative, so minus a negative is going to be plus x times 3i minus x times 1, then minus x times positive is going to be minus x times 3i. And then hopefully you recognize that if I have this times its conjugate, remember dividing, that's going to be the same as 1 squared plus 3 squared. If you don't believe me, multiply it out. So that's 9 plus 1, or this is going to end up being 10. Okay? Now, what happens? Like terms, plus x times 3i minus x times 3i. So we have an x squared minus x minus x minus 2x plus 10. So what this means is we do have a quadratic, right, that does have these two roots. And if we have these two roots, we could actually then figure out what the quadratic was. But it is a quadratic that has real number coefficients, because the imaginary actually cancel out. So that's how you find roots, and that's also how roots are related. That is finding complex roots, and how the complex roots are related. If you have one, then you have the other, and that is the conjugate. They occur in pairs, always.